In this video, we're going to look at another example of volumes by slicing. In this question, we have a solid that has a base in the xy plane, bounded by the curves y equals 2x squared, y equals 3 minus x squared. These are both parabolas. Y equals 2x squared is a parabola going up. Y equals 3 minus x squared is a parabola pointing down. Cross-sections perpendicular to the x-axis are semicircular discs with diameter of the semicircle on the base. And the question here is to find the volume of the solid. The first step is to find the points of intersection of these two curves. We have y equals 2x squared, and we have y is equal to 3 minus x squared. Let's make y equals y and solve for x. So we get 2x squared is equal to 3 minus x squared. Add x squared to both sides, and we get 3x squared is equal to 3. And divide both sides by 3, we get x squared equals 1. Take the square root of both sides, and we get root of x squared is equal to root of 1. But root of x squared is absolute value of x. Absolute value of x is equal to 1. And that gives us x equals 1 and x equals negative 1. Now, x equals 1, let's plug it into the parabola y equals 2x squared. This is a parabola going up. And we get y is equal to 2. So we get the intersection points 1 and 2, xy coordinates. X equals negative 1. Let's put it into the other parabola. Y is equal to 3 minus x squared. And we get y is equal to 2 as well. So we have negative 1 and 2 as the other xy coordinate pair of intersection. So the points of intersection are 1, 2, and negative 1 and 2. All right, the next step is to draw a picture of the base and the area slice, the cross-sectional slice. So you can see that we have the parabola going up, that's y equals 2x squared. And we have the parabola coming down, y equals 3 minus x squared. And we also have AB, this line segment, is basically the diameter, it's the diameter of the semicircle. The semicircle is coming out of the screen. We've drawn a two-dimensional version here. This is the area slice. And so basically, the point B has y coordinate. So let's do this formally. Point B has a y coordinate given by the top parabola, which is pointing down, y is equal to 3 minus x squared, for x between 1 and negative 1. And point A has the y coordinate given by the lower parabola, y is equal to bottom parabola, y is equal to 2x squared, for x between 1 and negative 1. So the line segment AB forms the diameter, it forms the diameter of the semicircular area slice. It has length AB, length of AB is the length of the diameter of the semicircle, is the top y value, which is 3 minus x squared, given by the y value of B, minus the bottom y coordinate, which is given by the y coordinate of A, minus 2x squared. And we're going to get 3 minus 3x squared. This is the diameter of the semicircular slice. So the diameter of the semicircular slice that is on the xy plane, that's given by the line segment AB, is equal to 3 minus 3x squared. Now, diameter is twice the radius, so the radius is half of the diameter, and that gives us the radius of the semicircular slice as 1/2 of the diameter, 1/2 of 3 minus 3x squared. All right, let's find a formula for the cross-sectional slice A of x. Since the cross-sectional slice is perpendicular to the x-axis, and these cross-sectional slices are semicircles with diameter, so diameter is equal to the length of the segment AB equals to 3 minus 3x squared. Radius is half the diameter, so the radius is equal to 1/2 of 3 minus 3x squared. Radius, half the diameter. All right, so the area, the cross-sectional slice has an area which is 1/2 the area of a circle because it's a semicircle. 1/2 pi times radius squared. That's 1/2 pi times radius, which is 1/2, times 3 minus 3x squared, close bracket squared. If we simplify this, we get 1/2 squared, that's 1/4 times 1/2, that's 1/8. So we get pi over 8 times 3 minus 3x squared, all squared. This is the cross-sectional slice as a function of x. These cross-sectional slices are perpendicular to the x-axis, so we're going to integrate in a direction of the x-axis to find the volume of the solid. All right, now that we have determined the area slice A of x, this will form the integrand of the volume formula. So the volume formula in the slicing technique is given as volume is equal to a to b, integral from a to b, a of x dx, and a is the lower x value of integration is -1, b is the upper x value of integration is 1, and the cross-sectional slices has area of the cross-sectional slices, which are semicircles. The area is pi over 8 times 3 minus 3x squared dx. Oh, there's no dx. So now we just have to integrate this, and we put it into this formula. Volume is the integral from -1 to 1, pi over 8 times 3 minus 3x squared, and integrate with respect to x. There's a dx. Once we integrate this, we'll have the volume of the solid. Let's do that. So the next step is to integrate the area slice to find the volume. Volume is integral a to b, a of x dx. A is equal to -1, b is equal to 1, and the cross-sectional slice a of x is equal to pi over 8 times 3 minus 3x squared, all squared. So the volume is the integral from -1 to 1, pi over 8 times 3 minus 3x squared, all squared. Let me write this better, to the power of 2, dx. Now, you will notice that the integrand is an even function. That means it's symmetric about the y-axis. So we can take a shortcut and say this is equal to 2 times the integral from 0 to 1 and simplify our computations. Pi over 8 times 3 minus 3x squared, all squared dx. And we can do that when the integrand is an even function. What I mean by an even function, of course, is f of minus x is equal to f of x, symmetric about the y-axis. So the two portions are essentially the same. They have the same area, so to speak. So we can just take 1/2 of the area and multiply by 2. That's what we're doing. So the volume is equal to, well, pi over 8 is a constant, passes through the integral and multiplies by 2. So we get 2 pi over 8, that's pi over 4. Integral from 0 to 1, 3 minus 3x squared, all squared dx. So we get pi over 4. Let's open up the integrand and fold it all out. 3 squared is 9. Minus 3 times minus 3 is minus 9 times 2, you get minus 18x squared. Plus 9x to the 4th, close the bracket, and integrate with respect to x. So we get volume is equal to pi over 4 times, let's reverse the power rule. So what is the antiderivative of 9? Well, that's just going to be 9x, because derivative of 9x is 9. What is the antiderivative of minus 18x squared? We get minus 18 x cubed, add 1 to the exponent, divide by same. We're applying the reverse of the power rule, of course. Plus antiderivative of 9x to the 4th, that's 9, x to the 5, divide by 5. Evaluated from 0 to 1, now we apply the fundamental theorem of calculus, and we get pi over 4 times the upper limit, which is going to be 9, minus, put 1 in for x, we get 18 over 3, that's 6, plus 9 over 5, minus, and put 0 in, we get 9 times 0, that's 0, minus 6 times 0 cubed, that's 0, plus 9 over 5 times 0 to the 5, that's 0, it's all 0. So the volume comes out as pi over 4 times 9 minus 6 is 3, plus 9 over 5. So we get pi over 4 times, take common denominator, that's 5. 1 goes into 5 5 times, you get 5 times 3, 15, plus 5 goes into 5 1 time, and times 9, 15 plus 9, we get 24. In the numerator, 24 divides by 4, and we get 6 pi over 5. If we decimalize this, the volume comes out to be approximately 3.77. That's the volume of the solid by using the slicing technique. All right, thanks. I need to make a slight correction on step 3. Here we have the cross-sectional slice as pi over 8 times 3 minus 3x squared. It should be all squared because the area is 1/2 times pi times radius squared. So we should have all squared here. All right, thanks.